Hello friends, myself Dr. Pramod Musrif from AISSMS Institute of Information Technology, Assistant Professor in Engineering Physics. Today we'll see the classification of solids. The content that are covered in today's session are introduction, semiconductors, energy bands in solids, conduction band, valence band and forbidden gap, insulators, conductors and semiconductors. Around 1947, transistors were invented by the scientists William, John, and Walt, and they have been awarded for a Nobel Prize for their invention. Before Second World War, vacuum tubes were used in the process of electrical signal generation, amplification, transmission, and reception. But after the invention of transistors in the electronic devices, the vacuum tubes were replaced. A solid-state electronic devices are mainly consist of the semiconductor materials. The semiconductor materials have the resistivity between good conductors and insulators. The resistivity of semiconductors is in between 10 to the power minus 2 ohm meter to 10 to the power plus 4 ohm meter at room temperature. But as temperature varies, this resistance varies. So resistance in semiconductor decreases with the increasing temperature, and this is contrary to the metallic conductors, for which resistance increases for the increasing temperature. The elements semiconductors are classified as silicon, germanium. Germanium and silicon are the most commonly used semiconductors. If you go for the energy bands in solids, if you go for the single atom, then the energy levels are discrete. That is 1, 2, 3, 4 and so on. Now if you go for isolated atom, that is silicon atom, whose atomic number is 14, then 1s2, 2s2, 2p6, 3s2 and 3p2. This 1s, 2s, 2p electrons are closely bound with the nucleus, whereas 3s and 3p are loosely bound and they are in the outermost shell of the atom. So these electrons are called as valence electrons, and the innermost electrons, that is 1s, 2s, 2p, are called as core electrons. So, and the above energy levels which are permitted above the valence band are called as conduction energy levels. In solid, if you go for the solid material, all the atoms are closely and systematically arranged, and due to this, the energy levels of the individual atoms will be influenced by the neighboring atoms. And therefore, instead of the individual energy levels, you will get the closely packed energy levels, and which are called as energy bands. For example, if we go for the 28 gram of the silicon, it will contain 6.023 to 10 to the power 23 atoms, that is Avogadro's number. Now here, if you go for the single atom, that is 1 number is written, energy levels are E1, E2, E3. If you go for 2 atoms, then the energy level of 1s, that is E1, or 2s is E2, and outermost level is E3 is shown for 2 electrons it is shown, same way for 3 electrons it is shown, and same way for that if you go for 10 to the power 23 atoms, then these energy levels are coming very close to each other. Rather, we can't differentiate between these two levels, and energy levels are in the form of bands. The valence band may be partially or completely filled, and the band cannot be empty. In some materials, valence electrons are loosely attached to the nucleus. So even at room temperature, some of the valence electrons leave this valence band and they go for these electrons are called as free electrons. These free electrons are responsible for conduction of the electricity, or these are known as conduction electrons. This band occupied by these electrons is called as conduction band. This band may be empty or partially filled. Now energy levels of the silicon atom. So as I have told you, 1s, 2s, 2p is our core energy levels, 3s and 3p are valence levels, and above 3p the all above other levels are called as conduction levels. Energy bands in silicon crystal. If you go for the band structure, then completely filled band shown by red color, valence band is shown by yellow color, and conduction band is shown by the green color. Now, since there is a difference between the energy bands, valence band and conduction band, so for silicon, the band gap is 1.11 electron volt, and this is called as forbidden energy gap. There should be lower band should be valence band and upper band should be conduction band. The separation between the valence band and conduction band is known as forbidden gap, and if electron is to be transferred from valence band to conduction band, external energy is required, which is equal to the forbidden energy gap. Now this is forbidden energy gap as shown in the. For insulator, this forbidden energy gap between valence band and conduction band is very large, whereas for semiconductor this gap is very small. So if you supply a large amount of energy, it is not possible to take the electron from valence band to conduction band. Whereas for semiconductor, this band is very small, and if you supply even very small energy, these electrons can move from valence band to conduction band. And for conductors, this conduction band and valence band, they are overlapping with each other, so there are already electrons are available, free electrons are available, which are in conduction band. So even at room temperature, you can use these electrons for the conductivity. Same has been explained here, that comparison of insulator, semiconductor and conductors. Thank you.